Good afternoon, all of you. Here, Digambar Londhe, research scholar from VNIT Nagpur. I'm presenting my work related to an event-based analysis of vegetation variation and its teleconnection with Enso and IOD. So the vegetation is the most important parameter and which is very quickly affecting due to the climate change. Suppose there is a drought, the first thing which is affecting is the vegetation. If there is a flood or when there is a good precipitation, the first thing which is affecting it is the vegetation. So it is very important to analyze its dynamics in connection with the Enso and IOD. So Enso and IOD are those climatic phenomena which are affecting the climatic pattern or climatic shift in the overall world. So these are the contents which I'm going to explain. So coming to the introduction, so this study analyzes the event-based vegetation responses to Enso and IOD using MODIS data. Then the diverse vegetation patterns are coupled with the annual shifts in vegetation photosynthesis activity lead to the fluctuation in vegetation phenology. And these impacts and teleconnection of the Enso and IOD on vegetations are analyzed utilizing remotely sensed NDVI data. So this is the study area. The study area is the upper Bhima subbasin, which is the one of the subbasin of Krishna River. And these are the micro watersheds, which are seen in this figure. So in this watershed, there is a Sahyadri mountain range, which controls the monsoon precipitation, which contribute to the highly diverse climate within the study area. So the total geographical area of this study is 46,000 square kilometer. So these are the data sets used and the methodology. So the data used is the MODIS data mod 13 C2 data product, which has the spatial resolution of 0.05 degree and the temporal resolution of 16 days. So this is the equation which explains how the NDVI will be calculated by using the bands which are recorded by the remote sensing data. So coming towards the Enso and IOD, so there are two phases in Enso and two phases in IOD mainly. Actually, there are three phases: El Nino, La Nina, and neutral. But neutral is the phase which we are not studying. So El Nino and La Nina events. So El Nino is nothing but the warm phase of the Enso, and La Nina is nothing but the cold phase of the Enso. So depending on the sea surface temperature, these two events are defined by the scientists. So when the average sea surface temperature is, suppose in a year there is a sea surface temperature which is above average sea surface temperature, then that event will be called as a El Nino event. And if that temperature is below sea surface temperature, average sea surface temperature, then that event will be known as the La Nina event. So based on the oceanic Nero index, suppose for the continuous 5 years, it is more than the 0.5 or less than the 0.5, less than minus 0.5, then those events are considered as a El Nino event and La Nina event respectively. So this is for the positive and negative IOD events. So similarly, as Enso events are related to the sea surface temperature, IOD events are related to the oceanic water. Suppose there is a cold water which is pushed toward the eastern Indian Ocean, then that event will be known as a positive IOD event, and vice versa, that will be the negative IOD event. So based on these events, the monsoon cycle within India and Australian coastal line will be controlled by these events. So similarly here in the for considering positive IOD events and negative IOD events, this dipole mode index is used to identify the positive IOD phases and negative IOD phases. Suppose there is a DMI value which is more than 0.4, then that will be known as a positive IOD event. And if that is in opposite, if that is a less than minus 0.4, then that will be known as a negative IOD phase. So as the study is related to the event based, so the events are calculated based on the ONI values and DMI values. Suppose in the ONI values, in case of Enso, July 2002 to February 2003, for continuous period, the ONI value is more than 0.5. So that will be the considered as a El Nino event. So these are the events which are considered for the analysis. So coming towards the NDVI data preprocessing in ArcGIS, the mod 13 C2 data product has been downloaded and preprocessed in the ArcGIS software. So the preprocessing includes the conversion of the data into the vector formation, then vector formation to the classification, then classified NDVI values are according to the NDVI values, the classification has been made as a less than 0.3 NDVI, 0.3 to 0.5 NDVI, and greater than 0.5 NDVI. So these classifications are such as sparse vegetation, moderate vegetation, and dense vegetation. To understand the homogeneity of the NDVI values, so these three classes are considered for the analysis. Coming towards the results, so the spatial variation, first I'll show this figure. So this is the spatial variation of vegetation NDVI during El Nino events and La Nina events. So we can see that the El Nino event, which is the warm phase of Enso, it is affecting largely in the vegetation. That red color indicate that the very sparse vegetation, which has the NDVI less than 0.3. And in La Nina event, we can see that red portion is reduced, and in last La Nina event, which is very recent, recent La Nina event, which is from August 2021 to January 22, which is showing dense vegetation. Also, it has been observed that the seasonal effect has been seen in this vegetation vegetation outputs. So in that last phase, we can see that event has been started from August, which is a monsoon, to the January. So that seasonal effect is also considered. So these are the percentage area within the study area which is calculated for each class. Here we can see that in El Nino event and La Nina event, both the event, the moderate NDVI is major area is covered with the moderate NDVI. But in El Nino event, we can see that the sparse vegetation has the maximum area as compared to the La Nina events. So this is the spatial variation of vegetation over the study area during IOD events. So IOD events as considered the positive IOD years and negative IOD years. So these IOD years are considered which are given by the Bureau of Meteorology Australia, and also those DMI values. So here actually many researchers are concluded that positive IOD is affecting India in positive manner, means they are saying that the positive IOD causes flooding in India. But in this study area, we can see that during positive IOD years, that southern portion of my study area, it is having very less vegetation. Means it is very sparse vegetation. So we can see that in this study area, it is not affecting positively, as many researchers have concluded. And in negative IOD years, we can see that the moderate vegetation, many of the large area is covered by the moderate vegetation. So these are the percentage area which are calculated from the spatial variation maps. Here also we can see that the major area is covered by the sparse vegetation, the moderate vegetation, and sparse vegetation is more during positive IOD events as compared to the negative IOD events. So these are the conclusion of my study. The study analysis, the comprehensive assessment of response of vegetation to ENSO and IOD events. So while analyzing, it is observed that the El Nino event, which is the warm phase of ENSO, has predominantly negative impact on the study area as compared to the La Nina event. And similarly, it is observed during the IOD events, which is positive IOD event is affecting negatively as compared to negative IOD events. And the major portion in this study area, it is actually the upper Vima sub-basin, which has the 5 agroclimatic zones. One is the Western Ghat zone, then there are 2 transition zones, and then major area is covered by the drought-prone zone. So in that drought-prone zone, the vegetation is majorly affected by the El Nino events and positive IOD events.
Okay, thank you. One more, the values of NDVI
Classes.
That's of the actual NDVI or the NDVI annually?
No, those are the actual indicators.
So the difference years if you are considering those are not necessarily from the same time, right? Can be long. For anything purposes, to make sure that the signal effect is not coming into place, we also need to subtract the signal.
Actually, that paper is already under consideration, which I did the study related to the by considering the seasonal analysis.
Hello, good afternoon, everyone. My name is Vaibhav. I am a PhD scholar at Indian Institute of Technology, IIT Indore. Today, I am going to discuss about the topic investigating the role of horizontal winds in understanding the extreme precipitation event, a case study of 2018 Kerala floods. So, in recent years, there has been various studies that estimates that there is an increasing trend in the global precipitation, and they attribute that warming climate is an main factor that results in the available of the higher precipitable water. And the IPCC report 2000 and 2002 and 2007 also emphasizing in understanding the extreme precipitation event. So there is a recent study by Samantha, which uses the 72 years of IMD global gridded IMD gridded rainfall data over India. So they study the interannual variability of the daily rainfall, and they also consider the interannual variability of the extreme rainfall event. So they consider a threshold of 100 millimeter. So wherever there is a rainfall of 100 millimeter or more, they count the number of events, and they see that there is an increasing trend in such kinds of extreme rainfall event. So when it comes to the extreme rainfall event, so Kerala is one of the most flood-prone area because of its geography and topography. So there are, we can see here that there is a Western Ghat on one side of the Kerala, on the right side. And there are various studies that relates the orographic lift. Orographic lift further enhance the precipitation event. So this Kerala flood 2018 was a very devastating flood in the state. So there has been various studies that study the various parameters like the synoptic condition, moisture transport, and vertical velocity. But there has not been much studies which uses the Doppler weather radar or any other ground-based measurement. So since the winds plays an important role in such kinds of events in transporting the mass, momentum, and moisture. So when we say that the wind observation, so there are multiple sources we can get the winds. So satellite-based observation, radio sound observation, and the model winds. So satellite observation, we can get the scatterometer winds also. Recently, ISRO launched an OceanSat-3 satellite that gives the surface level winds. And these winds will get at the surface level, and they have wind variability when there is a heavy precipitation. And when it comes to the radio sound winds, so we get twice a day at 0 hour and 12-hour UTC. And we have other model winds like NCMWRF and ECMWRF provides the winds. But they have a limitation of the limited spatial coverage of 9 kilometer and 25 kilometer, depending upon the location and region you are using. So in that case, the Doppler weather radar plays an important role, and India holds a good network of Doppler weather radar, around 37 Doppler weather radar. So Doppler weather radar basically provides the three-dimensional volumetric observations of radial velocity and reflectivity. So these observations are high in spatial and temporal scale. So every 15 minutes, we can have a observation, a 3D observation in dual polarization mode. So in past, there has been various studies that uses the radial velocity. So Doppler weather radar basically works on the Doppler effect. So it only measures the radial component of the velocity of the precipitating particle. So the past studies shows that we can get the horizontal or basically the local wind field using the uh, radial observation. So that's the whole objective of the present study, that how we can use the Doppler weather radar wind observations, radial velocity observation in order to estimate the horizontal wind fields. And the radar is located at the Tumba, the rocket launching site at the 8.5 degree north and 77° east. So the in order to briefly say about the data sets that are used, so the IMD graded daily rainfall data that is at 0.25 spatial resolution is used, and the radius on the observation is taken from the University of Wyoming for the Thiruvananthapuram station that is nearby the radar location. That is the nearest site available. And the Tulse Doppler weather radar data is used. So the data is used in PPI mode. So PPI mode basically means that the radar scans the concentric circles and the observations are available on the conical surface. And there are these are the parameters that are listed. So the Doppler weather radar can, this Tulse radar can can work in the two modes. One is the single PRF mode and one is the double PRF mode. So in double PRF mode, the resolution is 150 meter that we are using the double PRF mode only. And in that case, the maximum range is about 240 kilometers. So the methodology is briefly described as a flowchart here. So first of all, we have the Doppler weather radar radial velocities. So these are the raw radial velocities. So whenever we have Doppler weather radar observation, then because of the surrounding, we can have some kind of clutter. That clutter means that some artifact is there, if aircraft is there, or if some fixed target is there, then these are attributed as clutters. So in order to use the Doppler weather radar observations, we need to go for the quality control. So quality control basically involves two main steps. One is the clutter correction and another is the velocity dealiasing. So velocity dealiasing means that whenever this, as I already told, that this is based on the Doppler effect. So based on the maximum velocity that the radar can measure, so beyond that velocity, if the particle has that velocity, then that velocity will be underestimated. So that problem is known as the velocity folding, and we need to apply corrective measures in order to deal with this challenge. Once the data is quality control, then we are applying the two methods that are used to generate the winds. One is known as VAD method. VAD is known as velocity azimuth display method. That gives the 3D, not 3D profile, that gives the vertical profile over the radar only. And then we are also using a method that is given by Zhu et al. 2006, that is known as single Doppler method. So that gives a 2D winds, but that on a conical surface. So where basically the idea is that if we have at a constant height and constant range, there will be a circular observation. So when we plot these observations at as a azimuth, then we'll have a sinusoidal nature, and then we can use the Taylor series expansion in order to calculate the local wind field parameters. But there is a limitation of this method, that this can only gives the profile over the radar location only. And in order to have a comprehensive 2D analysis, we can go for another method that is known as velocity volume processing. So in literature, the velocity volume processing method has several disadvantages. Like this method involves estimating the linear parameters, but this considers that the wind fields are linearly varying, but that is not always the case. So there is a study by Zhu et al., as I already mentioned, that they uses 2D cross covariance functions in order to estimate the wind fields at a conical surface. So they use the background error covariance method while using the VAD winds as an initial guess. So in order to come to the results, so first of all, we analyze the rainfall, IMD graded rainfall data over the Kerala region, averaged from 75 degrees to 77 degrees and 5 degree north to 12 degree north. So it shows that the peak rainfall was around 15th of August. And the spatial distribution of the rainfall shows on the right hand side that almost most of the districts having a rainfall of about more than 200 on 14th and 15th of August. So in order to understand the precipitating system, we also create a PPI plot of the radar reflectivity. So as we can see that the GIF you can also see from the GIF that the system is moving southwesterly. And one of the interesting point here is that the systems are building on the over the Arabian Sea and moving towards the southwest. And we can see that at 7:05 UTC, that second row, second plot, that there is a frontal system, means a curve like of structure is there, that is a frontal system, and the maximum reflectivity observed was about 40 dB. So in order to investigate the structure of the precipitating system, we also create a max Z plot. So max Z plot means that we have reflectivity observations. It's a 3D observation. So whenever there is a maximum reflectivity, we have plotted that. So you can see the top panel of this plot shows the variation of reflectivity along with the longitude, and this shows the variation of reflectivity along the latitude. So we can see that there was a high reflectivity cloud of about 10 kilometers at that time that results in such kind of heavy precipitation. So as I already mentioned, the aim of this study is to understand the horizontal winds from the DWR observations. So we have created WAD profiles from 4:32 UTC to 12:07 UTC. And the corresponding radio sonde observations are also plotted in red, as you can see, for 12 hours 7 minutes. So in the lower troposphere, till 5 to 6 kilometers, there was a good match. But as we go away, as we go at a higher altitude, there are some mismatch. There can be multiple factors like the radio sonde observations and the DWR observation. They are not accurately time matched. Like the observation at radio sonde observation is at 12 hours, but the DWR observation is at 12 hours and 7 UTC. And what is the important point from here we can infer is that at the lower troposphere up to 6 kilometers, we can see that there was a high winds of about 5 to 50, 10 to 15 meters per second. So there is a study by Subramaniam Kumar. They also analyzed the same Kerala flood event using the ERA 5 data. So they conclude that there was a low level jet at that time that brings the moisture from the Arabian Sea to the landmass. Also, we can see that if we go from to the above 6 kilometers, that is still 8 to 10 kilometers, we can see that the wind speed is decreased, and this contributes to a decrease in the wind shear, and that contributes to the vertical development of the convective system that time. So after that, we also try to estimate the two-dimensional wind field. So you can see that on the left-hand side, that is the observed radial velocity from the Doppler weather radar. And on the right-hand side, you can see that the color represents the radar reflectivity, and the vector represents the retrieved horizontal wind fields, but at a conical surface. So you can see that if we are going far away from the radar, so it means that if we are going away from the radar, so these observations are at some particular altitudes. So it's like we are representing it in a 2D surface, but it's a conical observation. So we can see that, as you can see from this black curve, that there was a convergence at that particular point where there was a frontal system. So that convergence will enhance the development of the convective activity. So to conclude that this study analyzed the 2000 Kerala floods IMD graded data and the Doppler weather radar observation. So Doppler weather radar observation shows that the system were moving from the southwesterly direction from the Arabian Sea to the Indian landmass and have a precipitating cloud stopping to 10 kilometers. We also extracted the DWR reflectivity. So sorry, DWR derived horizontal winds, and these winds are compared with the radio sonde also. So the main factor that was that can be understood from this point, this study, is that there was a low level jets, as it was also seen from the ERA data also, and there was a wind shear apart from the wind convergence at the frontal system. So these study can be used in the regional modeling, because the yeah, that's right. Yeah. So at last, we would like to thank the MOSDEC for providing the Doppler weather radar data, and the University of Wyoming for providing the radio sonde data. And this work was supported by the Space Application Center, ISRO, and MOES NARL program. Conical wind, no, what I'm trying to say is that these wind speeds are not at a fixed altitude. These are at a conical surface. We are just reprojecting it. So this method retrieves on a conical surface. We are currently in a process of developing an algorithm that generates it at a different altitude. Hmm. Yeah, radial velocity. Velocity and yeah. So we apply the technique given by the Zhang. That is a 2D automatic wind speed correction, de-aliasing correction. So method basically it look for the continuity in the wind speed, that it should not abruptly change. Yeah. 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 Yes, yes, sir. Basically, sir, our aim is to develop a technique that can generate the horizontal winds from the Doppler weather radar. So that is just a test case that we are trying to implement, that what are the applications of these wind fields, and in order to validate it. Yes, you are correct that we can also look for the cases where there are no such extreme events. So we can analyze that also. Yeah. No.
Good afternoon, everyone. I'm Shivika Saxena, PhD scholar from GISL Motilal Nehru Institute of Technology, Prayagraj. And I'm giving my talk on the topic that leveraging multi-source Earth observations for high-resolution mapping of precipitable water vapor. So precipitable water vapor is an essential climate variable, and it's a very important precursor of rainfall in the weather forecasts. These are the contents of my presentation. So the figure one shows my study area, that is a portion of or in a small INSAR window in the state of Uttarakhand, which has a very complex topography with mixed climate patterns. So that is the major objective of choosing this area. And we have a radio zone station and GNSS station located at Dehradun in this small window. So the major objective is to integrate complementary techniques, that is GNSS and INSAR. By INSAR, I mean interferometric SAR. So complementary techniques integration used for generating high resolution PWV. So high resolution water vapor analysis can be done from a very limited, in an area where limited meteorological data sets are available. So INSAR actually gives us very important insights about the small scale variations in PWV, which can be apparent only in the high resolution maps in PWV. If we use high resolution temporal, high temporal resolution GNSS data, we might not be able to look at this information. So this information I will speak like the information, water vapor information from INSAR is actually turbulent mixing of water vapor that is coming here. And from our GNSS and other sources, we get the non-turbulent component. These are the data sets used. ERA5 dataset, reanalysis dataset, Sentinel-1A single look complex dataset, GNSS meteorological data, a MET file, and INSAT 3DR data, which gives us PWV. This is INSAT 3DR sounder data. So we have these datasets at varied resolutions. So we are trying to use a multi-earth observation in one scenario. So InSAR meteorology basically focuses on the phase difference that is obtained from an interferogram, which is the output of the InSAR processing. Okay, so interferogram is the visual representation of phase difference between two or more SAR images taken from slightly two different positions at different acquisition times. Okay, so phi int means the interferogram phase difference that can be divided into atmospheric phase noise, that is atmospheric phase screen, APS, and some other sources of phase difference like topographic phase and etc., and some noise. So our concern is the atmospheric phase screen phi ATM, which can further be divided into tropospheric delay as well as ionospheric delay. So I'm using Sentinel 1A SLC dataset, that is essentially C-band data. So ionospheric delay is very less. So we can ignore that here. Because of high frequency, ionospheric delay is actually inversely proportional to square of frequency. So we can ignore ionospheric delay, and we can finally focus on tropospheric delay, which will give us the water vapor information. So I'm converting my tropospheric delay can also be visualized in terms of two components. One is coming from the wet portion of the atmosphere, that is water vapor. One is coming from the dry portion of the atmosphere because of dry gases. Okay, so finally we reach to the water vapor component, that is phi wet. Now this phi wet is converted into differential zenith wet delay coming from the InSAR, and finally to our observable of interest, that is precipitable water vapor, differential precipitable water vapor. So the pi factor is used to convert ZWD into PWV, and this pi factor is a function of weighted mean temperature in the atmosphere. So we use TM models, our own designed TM model for Uttarakhand state from my previous work for this conversion for better accuracy. This is my overall methodology followed here. So basically, I started with the InSAR dataset. That is the main dataset used in my study. And I've selected few pairs for 6 months, March 2021 to August 2021. Then interferogram generation, that whole processing I went through in the software environment Snap. And then I did some enhancement like Goldstein filtering and multi-looking, all those things. And then finally unwrapped it. So the unwrapped information coming from the interferograms, differential interferograms, gives us the differential slant total delay. We arrive at the wet delay from the previous slide information, just like that. And the hydrostatic delay, that is the dry information coming, I have to remove it from the total delay to get the wet information. So that dry information, I'm taking it from the reanalysis dataset ERA 5. And then I finally arrive at the InSAR PWV. The interesting thing about InSAR PWV, differential PWV, is that it gives only us some partial information. It is not full. It is, it has that unwrapping of the interferogram has actually introduced some unknown bias to it. So we either have to calibrate it using other measurements to get us the real information, or we have to use some models to fulfill it, to bring us to the full atmospheric information. So I'm using the calibration method. So InSAR differential PWV is calibrated using the data from GNSS. So from GNSS met information, the signal delay, wet signal delay, I developed my GNSS differential PWV at the same acquisition times of the interferogram generated. And then I calibrated, and then finally I validated using the InSAT 3DR PWV data. Okay. I also do some pre-rainfall event validation change analysis using Indian Meteorological Department, IMD, rainfall data, gridded data, to see just before rainfall, what was the PWV scenario, which was captured in the image just one day before. So PWV and rainfall are really correlated with each other. If there is a rainfall going to happen, then PWV is going to give very high values. Okay, so that kind of pattern we have also seen in our results. So this is the calibration of INSAR PWV using GNSS meteorological data. So what we're trying to do here is that this is the GNSS station here, and this is the cutoff angle used in the GNSS processing. So this, along with the 1.5 kilometer of lower tropospheric height, we are trying to make a GNSS cone, and this and the INSAR pixels lying within this GNSS cone are averaged and then added to the the bias is added to the these are calibrated using the PWV GNSS data. These are my results. So the RMSE between the INSAR and the INSAT values for differential PWV lies around 3.6 millimeters, which is fairly satisfactory for my case. And the RMSE between GNSS and INSAR values is 0.7569 millimeters. This is fairly low and good for my case study. We can see that this date, 14th August and 26th August, this is the differential PWV value from the GNSS, from INSAR, from INSAT, and this is a very good results we are getting for the pre-event date. So the event actually happened on 27th August. So the picture was captured, atmospheric picture was captured in the INSAR data from 26th August, and we can see good results. These are my high resolution maps generated from the from using the high resolution INSAR data calibrated using GNSS. So fairly high values of PWV we can see in the next image, which shows a scenario just before a rainfall event. So excellent agreement is witnessed among all the data during the 14-26 August duration, which represents the pre-event scenario. The rainfall happened was 90 millimeter, which is a good amount, on 27th August 2021. So that event has been captured in INSAR data. And as of now, for future work, after I submitted this work, I've developed a lot on this. So I finally arrived at all this data is differential, means the PWV values are actually the difference between two acquisition dates. So what we want at the user end is the absolute value. So absolute PWV maps now can be generated at a very high resolution data using multi-temporal INSAR techniques, which I have attempted and I'm about to write and submit. We have got good results for that. And the calibration thing that we did in here, I have actually developed zenith water vapor delay models for capturing the non-turbulent portion, which is not captured in the INSAR data. Thank you. The one that was openly available to me was only one station at Dehradun in my study window. But we can utilize actually the whole state. I'm working on the whole state, which has currently 13 GNSS stations in the course network developed by the Survey of India. That I'm currently working on. So this was the test window I started my work with. Now I've developed the work. Yeah, APS. Yeah, that's what I'm developing on that now. Yeah. Yeah, very nicely. Yeah. That's what I've moved on to multi-temporal now.
It's possible to predict in case of an extreme event exactly how much rainfall will take place based on the
So that's the thing about InSAR that period is right now in my case it's 12 days because I'm using Sentinel-1A data. The good news in the presentation in the plenary session was that it is going to be reduced to 3 days. So good news for meteorology using InSAR because yeah, that is a drawback for InSAR data right now. It could be, we were actually thinking about using 1A and 1B that could give us a revisit period of 6 days. So that was a possibility. It had various issues related to it in the processing. But yeah, the thing is that, yeah, if we are lucky enough that rainfall event ho raha hai and we are able to capture it, um, because the rainfall event has PWV values variation in the temporal vicinity of that event. So even during the rainfall, the PWV values would be higher. It will not suddenly drop. And even after the rainfall event, there might be some residual PWV, which would be showing that rainfall event. So all those things, possibilities are there to capture it. And if we use the models for zenith, wet delay, and PWV that I'm talking about, combining InSAR and we can come up with a multi-earth observation model, which we can actually use at our, you know, what you will say, at our end, like at our freedom. I don't want to. Thank you.
impact of jet stream feature on precipitate north area during ski landing during the South Asian earthquake of 1980.
I don't remember which one. This one. Yeah. Introduction. I come from Spain. First of all, I would like to acknowledge the different proposals of this work that we have been developed together in the last year. So, okay. So as everybody knows, one of the main effects of the climate change nowadays, among the other things we have seen here in this session, is that the increase in the number and the severity of the wildfires. So here, for instance, you see one of the news we had about the fires that took place here in India in one of the newspapers in Spain. So just to give you an idea of the importance and how these news are affecting all the world, okay? So in essence, what we have observed in this particular case in 2022 of the world, but they, as I said, the wildfire activity has been in the last year. So our idea basically, first of all, to try to predict the extension of the fires of this extreme, because it has been shown that one of the main characteristics of these new fires and the threat of climate change is that they are increasing in size. So we wanted to study which are the processes governing the extension of this wildfire. So in a classical approach, normally in remote sensing, people, what they do is they take different variables and they try to predict the extension of the wildfire. But in most of the occasions, the people are, in this case,
what we were trying to identify is the importance of the jet stream into the extension of the wildfires, because one of the main effects of the climate change has been the changes into the jet stream, especially in the northern hemisphere. Okay, what is the jet stream? In essence, jet stream are the upper atmosphere winds. To put it simple, so what we have the areas of high pressure, we have the areas of low pressures. So this generates a lot of winds. So normally, in a normal situation, before many years ago, what we had is that these winds, okay, are more or less parallel to the equator. So one of the things that have created the climate change is a meandering of this border. So what we are observing is that high pressures are going to the north and low pressures are going to the south. For instance, one of the episodes which were important 1 or 2 years ago was the effect of very low temperatures in the US. We had temperatures below zero in the area of Texas, which is quite abnormal, okay? In Europe, we are suffering also in that case. This summer, we have this meandering effect that we had severe floods in Greece and in Spain, and in the middle of Europe, we have extremely high temperatures. So in this particular case, we want to see if the jet stream had an effect on the wildfires of that took place in India last year in 2022. So we wanted to try to get the impact of this variable. How do we want to do that? At the moment, as we don't know which model or which processes are governing all this, we thought that maybe machine learning approaches, because they are able to interact with nonlinear interactions, were able to extract not the model itself, but the importance of the different variables, okay? We didn't want to rely in a physical model, which may have some limitations with dealing with this non-stationarity, because in the past, we didn't have this. We have only these behaviors since a few years. Okay, so which is the data we have used? First of all, we have used for MODIS, we have used the extension of the fire. Huh? This is a classical variable. To study the jet stream, we have used the upper atmosphere's variables obtained from NOAA, and apart from that, we are getting other types of variables, other variables that, of course, are affecting the extension of the wildfires. We are using meteorological data for the EMCWF, is the European Climate Medium Weather Forecast Institute, is the institute in Europe for climate studies. We have using soil moisture and vegetation obtained from radiometry from one institution in Spain. We are getting land cover to see if the type of land cover is affecting also the extension of the fire, the elevation, distance to roads, just as a proxy of the human effects. And here you have the variables we have been observing: soil moisture, vegetation optical depth as a way to measure the presence of vegetation, vapor pressure deficit, as shown before, land surface temperature, anomalies in the upper atmosphere, elevation, and so on. And here you have which are the different resolutions. Remember that here we are dealing with one application, climate application. So therefore, we are not really concerned about doing that for the moment at very high spatial resolution. We wanted just to see which is the effect of these variables which determine the jet stream. So which are the area of study? We basically are considering between April and May 2022 here in India. So we are considering fires in India, in Pakistan, and Myanmar, which are these red dots plotted in here. So from there, what we had is, from MODIS, we had more than 30,000 affected pixels where we had the fire. So in order to simplify a bit the data and to facilitate the analysis, we binned the data at 1 hectare resolution. So we are considering fires and that level of resolution. Okay. And at the end, all this process end up with a little bit less than 1,000 fire events that we want to study, which is the effect of the different variables on the extension of these fires. How do we take into account the jet stream? So basically, for the different location of each fire, okay, what we have or what we make is a collection of temporal images with the different variables that basically consider the information of the jet stream. Basically, is the direction of the winds and the anomaly of the geopotential anomaly at the height of 500 hectopascals. So the idea basically is to see if also the temporal evolution of the temporal information of the jet stream affected the extension of the fire. Okay, because remember what we want to study is these winds and particularly the meandering effect due to the climate change. In which tool we are using that? We are using the different variables, classical land surface temperature, vapor pressure deficit, soil moisture, BOD, etc. Okay, of course, information about the jet stream. We are using the classical division, training 80%, testing 20%, and of course, our output, or the variable we want to predict is the extension of the fire. We have used a framework based on machine learning. Indeed, we are not interested into the technique, okay? We are interested only into the variable. So we were using support vector machine, 3 basis approaches, random forest, XGBoost, DBR, neural network. I mean, after this analysis, maybe we could go to more advanced techniques, but at the moment, we don't care about too much about which technique. We want, as I said before, to see the influence of these variables of the jet stream, which has been almost never considered. So how do we consider the effect of the jet stream? So here, what you see is the spatial-temporal composite of the 2 variables we are using for controlling or for measuring the jet stream, MCI at 300 hectopascals and delta Z for 500 hectopascals. So basically, what we were doing is considering the fire at T0. Okay, the fire takes place at this position. So what we were observing is that the evolution of the jet stream, we observed that approximately 6 days before the event of the fire, essentially 1 week, what we observed is that there is a big anomaly on the area. And this anomaly, what it prevents or what it makes is the condition of the meandering of the jet stream. So basically, with this, we can control where the top of the jet stream is going of this wave of the jet stream. Just to see with one example, okay? This is an actual fire, sorry, one actual state of the upper atmosphere. So here, in these areas, what you see here is the situation of low pressure. And here you have the idea or the areas of high pressure. So in a normal situation, we would expect the jet stream to be more or less parallel to the equator. Okay, so basically, the low temperatures will stop at this point, and the high temperatures stop at this point. But what happens due to the climate change? Essentially, the jet stream has become crazy, and the areas of high temperature are going up, and the areas of low pressure are going down. So what we are observing, basically, what these areas of high pressure is creating is what they are called heat domes. So here, what we show is the situation of the jet stream, land surface temperature, and vapor pressure deficit. So as you can observe, up to now, the people were using the land surface temperature and the vapor pressure deficit as a proxies to analyze the wildfire. Okay? But as we see, the conditions that are establishing these extreme temperatures or this extreme of these problems with the vapor pressure deficit is indeed the jet stream. So we have tested the different the different prediction algorithms to extend the fires. And here you have the main result. So the basic message of this slide is that if we include the information about the jet stream, which is indicated in blue in this plot, we increase the accuracy with which we estimate the extension of the wildfires. And we increase the accuracy at 10%. Also the errors, okay, are in here, and the errors are lower with the jet stream approximation. We don't, as I said before, we are not really interested into the tool. Here you have the 5 tools, okay, and normally we are considering the ESG because it's the best giving the results. Just the final results. We also did a segmentation on small, medium, and large fires, and what we see here is the following. With jet stream, the error in the low fires is very high, 24%, because the fires are very small, so you commit a lot of errors. But the important fires are the medium, which are 6%, and the large fires, which is about 9.42%. If we eliminate the jet stream, the error on the low fires increases to 26%. For medium, it increases to 6.62%, and for the large fires, it increases to 10.66%. So as we can see, including the jet stream, as a proxy for the extension, we improve the estimation of the extension of the fires. So just to conclude, we have used various machine learning algorithms, okay, to predict the extension of the fire, considering by the first time the jet stream information. And in essence, we can see that independently of the technique we are using, we are able to improve the estimation of the extension of the wildfire in about 10%. What we have not done is just to use the jet stream. We have used all the collection of the variables, all the variables. So therefore, okay, it is important to consider these variables because at the end, the physical effect that produces the temperature to rise, the problems with the vapor pressure deficit is indeed the jet stream, okay? For the future work, we want to use new machine learning techniques, which are a bit more accurate. So we want to use vision transformers, okay? And especially what we are doing now is to try to see if we see the same behavior in other areas. Indeed, we are now exploring this approach in the whole European continent. Our next step is also to explore in Australia, where you have extreme fires too, and in Canada, where you have big areas. And our idea is to see in all these areas the increase in the extension of the wildfires is governed by the jet stream. Okay, here I finish my presentation, and now I'm open for questions. Thank you. Yeah. It's 6 days before the fires. No, this is this is not in ground. This is in the upper atmosphere. This is the situation in the upper atmosphere. Yeah. No. Yeah, the heat down is because you have here the high pressures, the high temperatures. It's a kind of oven at the end. So basically, what it provokes is the increase on the land surface temperature. So the effect of the high pressures on the upper atmosphere is the increase of the land surface temperature. Honestly, I cannot tell you because the expert on this particular effect is Amir. Because he's a climatologist. Okay.
Okay, sorry to interrupt, but I think we're out of time, so you can please back up.
After that, we can discuss.
Okay, let's thank the speaker once again. And last talk now is Saxena and Digambar, numerical simulation of surface albedo and pressure over neutrally using a nested WRF model.
Back to paper 1.1. This no, yes.
Yeah, good afternoon, everyone. Today I here to present my preliminary work on the numerical simulation of surface albedo and temperature over New Delhi region using WRF model. These are my contents: introduction, research objective, introduction to WRF model, introduction to its workflow and model configuration, and some of my results. As we all know, surface albedo is just a ratio of the reflected irradiance from the hemisphere, and LST is defined as the land surface radiative skin temperature measured from the sensor direction. As you have all know, these two parameters are very much interlinked, as they determine the extent of how much energy is reflected out from the sun out to space. These two parameters are interlinked as they determine the energy out from the sun absorbed at the Earth's surface. So there is need of accurate simulation of these two parameters to monitor the climate and detecting trends. So for doing that, one such numerical weather prediction model is needed, and the WRF model is very much used by the various researchers in this field. So this is my research objective: to initialize the WRF model using suitable physics parameters in order to simulate these two parameters over NCT Delhi. So some of the introductions of the WRF model. As you have all know, a WRF model is a state-of-art meso-scale numerical weather prediction model designed for atmospheric research and operational forecasting applications. WRF model produce simulation based upon the actual atmospheric conditions, that is from the observations and or the ideal situations. So WRF model is provide a platform for the urban climate simulation by combining all the microphysics options, planetary boundary layer, radiations, and land surface canopy, all the meteorological parameters to predict or to simulate the meteorological parameters which we need according to our work. So coming to the simulation workflow and of the WRF model, first the initialization step of started with the inputs, that is static geographical data and gridded meteorological data, and these two graded inputs are used in the WRF model. First is and these two input configurations we not need to input in the model itself, and if we want, we can do that also. Starting from next step onwards, this GeoGrid executable file is to create the WRF domain. It may be one nested or two nested according to our study, and these are the input parameters which I have used in this study. And second is ungripped data executable. This ungrip is used to extract the meteorological data and its required fields in the input domain, which is generated by GeoGrid. Then this GeoGrid and ungrip is mixed and the we can interpolate this methodological data in the horizontal directions and the vertical directions of the generated domain by GeoGrid. This is all about the pre-processing steps in the WRF model. Now coming to the simulation part, then the input of the real executable and the after combining all those pre-processing steps, we come to the WRF simulation. This is known as the WRF itself. And these were the physics options selected for this study from the various literatures I have referred for this study area. And the physics options is basically used in simulation to update or to change the dynamics of the upper atmosphere, which we also don't know how the atmosphere will able to behave on that particular day. This is all about the simulation part. Then after that, we get the final results in the form of NetCDF format, and we can also do the post-processing part by visualizing the output from in any of the softwares in either in LCL viewer or Panoply. These are my simulation results. This is all about the domain itself, and as you have seen, the clearly high temperatures is indicated from the simulations, that is 296 Kelvin to 302 Kelvin. And I also related these results from the albedo part also, as you have clearly seen that the overall domain albedo is about 16%, and which is very much lower than the overall northern Indian albedo, which is about 24%. And I also validated these results, simulated results from the meteorological IMD stations, which is situated at the two locations in Delhi. And we have seen the overestimation from the simulated temperatures at about 3 to 4 degrees Celsius. And this is maybe due to the upper atmosphere conditions, which is taken care in this WRF model simulation. So coming to the conclusions part, this physics model is best suited for the simulation of temperature and the surface albedo in the specifically in the NCT Delhi region. But the radiometric quality of the results, it's at the very coarser side. To overcome this limitation, we have used a subset portion of the New Delhi region by using nested WRF capability. And in order to mitigate these high temperatures and to increase the albedo around the study area, the one more important factor which we can use is the use of refractive